Okay, this is Chem 1132, Week 1, Method of Initial Rates. We're going to solve a sample problem involving figuring out your rate law when given the data. Now, I just want to remind you that if you haven't had a chance to do this yet, you need to log into D2L and read the file called Algebra Review if it's been a while since you've done any sort of calculations involving exponents, because sometimes we will need to solve for a variable in the exponent. So please download this file, Algebra Review, from D2L. Okay, so here's a sample problem. Now I would have to give you this data. So here's my problem. I've given my reaction and I want to know what's the rate law and what's the rate constant for this reaction. So the first thing I need to do is I need to write the general form of my rate law. Rate equals K times I minus to the X times OCO minus to the Y. And what I want to do is I need to figure out a way to solve for X and to solve for Y. So the way I'm going to do this, I'm going to solve for X first. All right? So to do that, I want to pick a pair of trials where iodide changes and hypochlorite stays constant. So I'm going to pick trials 1 and 2. So we're going to write our information out. We're going to plug in experiment 1 into the rate law, and we're going to plug in experiment 2 into the rate law, and then we're going to divide them by each other. Okay? So rate equals K times I minus to the X times OCO minus to the Y. We're plugging in the rate at trial 1. We're plugging in the rate at trial 2. Okay, so that's where these numbers are coming from. So rate equals K, I minus to the X, OCO minus to the Y. And when we plug in our values, this 0.12 comes from the value here, and this 0.06 comes from the value here. This comes from here, and this comes from here. Now when you do the dividing, you notice the K's cancel, and this cancels. So it leaves me 7.91 times 10 to the negative 2 divided by 3.95 times 10 to the negative 2 is 2. It's very close to 2. And then 0.12 divided by 0.06 is 2. So I get 2 equals 2 to the X. So what number must X be? Well, X must be 1, right? Because 2 to the first is X. So now we know what the value of X is. We're going to do the exact same procedure to figure out the value for Y. This time I'm picking a pair where I want the amount of OCL minus to change and the amount of I minus to stay constant. Okay, because you want one of them to cancel out every time. So I picked experiments 2 and 3. Okay, so 0.06 and 0.06, 0.09 and 0.18. So again, rate equals K times concentration to the X times concentration to the Y. So when I plug in my rate for experiment 2, that's where this number comes from. When I plug in my rate for experiment 3, that's where this number comes from. Plug in my value, 0.06 and 0.06. Plug in my value, 0.18, 0.09. Again, anything that's the same is going to cancel. When you do your arithmetic, this divided by this is very, very close to 4. And this divided by this is 2. So 4 is equal to 2 to the Y. So what must Y be? Well, when you square 2, you get 4. So Y is 2. So now I know the value of X, and I know the value of Y. Rate is equal to K times I minus to the first times OCO minus to the second. And if I asked you what's the overall order of this reaction, you would say it's third order, right? Because you just add the exponents. But I still need to solve for K. So to get K, all I need to do is pick any one of my trials and plug the data in and solve for K. So I just picked experiment 1 because it's first. Okay, you could have picked 2, 3, or 4 and you get the same answer. So I just picked trial 1. All right, so rate equals K times I minus to the first times OCO minus to the second. So here comes my value from trial 1. Rate equals K. Now K is what we're solving for this time. 0.120 moles per liter comes right here. And 0.18 moles per liter squared, right, I'm squaring it, comes from right here. All right, so now we're just going to do some arithmetic. This equals, we just did multiply this by itself and then multiply it by this. So that's what we get, and then K is what we're solving for, so we divide both sides by 0.0039. So K ends up being 20 liters squared per mole squared second. And now we know the specific rate law, so the specific rate law is right here, and we know the value of K, so we're all finished.